strictly following the Pearson textbook page by page, so that if at the end of the class you want to once reflect back, you can read that. So what is a refraction? Refraction is the bending of a ray of light when it travels from one medium to the other at the medium of separation. Okay, so there are laws of refraction. First law was the incident ray, refracted ray, and the normal at the point of incidence lie in the same plane. This was the first one. And the second one was if we have medium 1 and medium 2 and a ray of light travels from one medium to other, then medium 1, if it is rarer and medium 2 is denser, then the ray of light bends towards normal. The ray of light bends towards normal. And then we have angle of incidence and we have angle of refraction. Angle of incidence is greater than angle of refraction. This is one of the laws. And the vice versa also is true. If the ray of light travels from denser medium to rarer medium, the ray of light bends away from normal. Denser meaning is optically denser. Optically denser means greater refractive index. These are rarer medium means optically rarer, and optically rarer means whose refractive index is very less. Very less means compared to the other medium only. That was second law of refraction. Third law of refraction was the Snell's law. What is the Snell's law? Snell's law tells that when a ray of light travels from one medium to the other, at the medium of separation, the ray of light bends. That bending depends upon what terms and conditions. That bending depends upon the refractive indices of the two mediums, the medium through which the ray of light passes, the two mediums. So that guidelines Snell's law tells. So what is Snell's law? Snell's law states that for a color of light, when a ray of light travels from one medium to the other, say we have a rarer medium and we have a denser medium, say for example, and this is that normal, and this is that normal. And when the ray of light travels from rarer medium to denser medium, it bends. Okay, not necessarily. Snell's law is not related to which medium to which medium. So this is angle of incidence, this is angle of refraction. Okay, so what is Snell's law? Snell's law states that for a color of light, when a ray of light travels from one medium to other, the ray of light bends, B-E-N-D-S, bends at the medium of separation. What is medium of separation? This line that demarcates rarer and denser, that is called medium of separation. Okay, so it bends such that the sine of angle of incidence to sine of angle of refraction is a constant, and that constant is called a refractive index of second medium with respect to first medium, which we will write it as a mu2 1. Our books write n, our book is also writing mu. Okay, this one. So mu2 by mu1 means what? Refractive index of second medium divided by refractive index of first medium is equal to sine of angle of incidence. Angle of incidence is there in the first medium, means second medium information, means you see, this is about second medium, this is about first medium. Sine of angle of incidence is in the first medium. Angle of refraction is in the second medium. So rarer is first, denser is the second medium. Okay, so like this. Snell's law, just have patience. I'm reciting it once again. What is Snell's law? For a color of light, when a ray of light travels from one medium to another, the ray of light bends at the medium of separation such that the ratio such that the ratio of sine of angle of incidence to sine of angle of refraction is a constant. That constant is called refractive index of second medium with respect to first medium. That's all. This is Snell's law. All right. Okay, that means, in a way we are trying to understand that sine of angle of incidence to sine of angle of refraction, that ratio is actually depending upon the ratio of refractive indices of the two mediums. Okay, so this is the laws of refraction. This yesterday we did. Then here we were introduced to the word refractive index. Refractive index will denote with the letter mu. If we just write mu, its meaning is it's absolute refractive index. What is absolute refractive index? Absolute refractive index is refractive index of any medium with respect to air. And here people don't remember, but very few things we can remember. Refractive index of air is 1 approximately. Refractive index of water is 1.33. Refractive index of kerosene is 1.44. Refractive index of, say, diamond is 2.42. Air refractive index is the lowest. Diamond refractive index is the highest among the substances. Okay. So what is refractive index? Refractive index is actually a property. Refractive index is actually a property of any medium, any transparent medium. Refractive index is the property of any transparent medium. Why I said transparent medium? Because the ray of light has to travel from one medium into that transparent medium and exit. That's why. So it's a property of any transparent medium that decides the optical density, that decides its optical density. So property of any transparent medium, which property? That property is called optical density. Optical density. So in a way, refractive index of a medium and optical density of a medium are synonymous. Synonymous means sometimes when you don't want to use the word refractive index, you can use the word optical density. Means when you say refractive index is more, it will be understood that, oh, it is optically denser. Optically denser means what? A ray of light can pass through that medium slow because it is so denser that speed of light is reduced. Okay, so mediums with more refractive index will be optically denser. And because it is optically denser, a ray of light speed reduces. Speed reduces, that's all. Okay, so this is what it means. And then how do we define refractive? That's a general information. What is optical density? Optical density's other meaning is refractive index. Okay, so I'm not repeating many number of times. You must have understood by this time. Okay, so you understand that it is a property of every transparent medium. Refractive index is equal to optical density. Or I'll do one thing, it's not optical density. You take it as it is a directly proportional to optical density. Any medium which is optically denser definitely has a higher refractive index and vice versa. And how do we define refractive index? For defining refractive index, yesterday I wrote 3 formulas. Today I want to extend and put one more additional term to that. Refractive index actually, according to Snell's law, is the ratio of sine of angle of incidence to sine of angle of refraction. This is a refractive index of second medium with respect to first medium. So this happens to be the one of the definitions. And then refractive index is also the ratio of a speed of light in vacuum or air. Vacuum or air are not closer things, but approximate. When speed of light is itself in an approximate number, air is supposed to be less denser thing, close to vacuum, like that. Not necessary what I said just now. But ratio of speed of light. Refractive index is the ratio of speed of light in vacuum or air to speed of light in a medium. And speed of light in vacuum or air is 3 into 10 to the power 8 meter per second. Speed of light in a medium depends upon the question itself. Okay, we don't know what it is. So this is the second formula that we saw yesterday. And then one more formula for refractive index. Refractive index, actually, when we place a coin inside a tumbler or a stick inside a tumbler containing some liquid, water or oil, the stick appears to be bent. That means the part of stick which is in the air, the part of stick which is immersed in that liquid, they don't appear to be in a straight line. That's why that, because the ray of light travels from the interior of the liquid, and then at the medium of separation it takes a bend, and then it reaches our eyes. And because a refraction occurs, for us, that stick or the pen that we kept immersed in the liquid doesn't appear to be a straight line. Similarly, doesn't appear to be straight. Similarly, if you place one experiment, they say, no, you put a coin in a bowl and go close to it and you look into it. The coin is visible. Now you start walking away from the bowl, which consists of the coin. At a certain distance, up to a certain distance, you can see the coin. But if you further travel, the bowl's edges will be the obstacle and you can no more see the coin. Then the question is, how can you see the coin without going close to it? You understood what I said just now?
Yes, ma'am. I seen this experiment in one video.
You know this experiment. No? So what they do is, in that bowl, they put some water or any liquid. And when you put a water or liquid, that water or liquid will not raise the coin, just like the crow story. It's not like that. But what happens is rays of light from the coin take a bend at the medium of separation and reaches that observer who is at a particular location. And refraction allows the coin. Refraction raises the height of coin, an optical illusion, in fact, and the person is able to see. Okay, so refractive index, one more formula is real depth to apparent depth. So these are the three formulas yesterday we discussed about refractive index, okay, about the medium. Then you see one point I want to discuss, though, however, we are going to come across the topic refraction through glass prisms. Okay, so there we can't come back to this topic. So what I'm doing is I'm writing that refractive index of second medium with respect to first medium is mu2 by mu1. And from the, this is the first formula, this is the second formula, say for example, and this is the third formula. And then from second formula, refractive index and speed of light in the medium are in inverse relation. So here I can write mu2 by mu1 as v1 by v2, means speed of light in a particular medium by speed of light in the other medium. Okay. This further I can write it as sine of angle of incidence to sine of angle of refraction. And then what happens here is, when ray of light travels through a glass prism, then the ray of light, when it travels through a glass prism, the ray of light deviates from its path. And there we will introduce a term called delta, which is called angle of deviation. Actually, the next topic is refraction through glass slab, and after glass slab prism. So then we'll, however, come to this point, but one concise formula let's have and we move out of this topic. So delta is the angle of deviation. When a ray of light travels through a prism, it deviates from its path. As a result, it breaks down into that Vidgyor. So delta is that deviation from the actual path of the ray of light when it passes through a prism. So angle of deviation is actually equal to angle of incidence plus angle of emergence minus angle of the prism. Okay. And then we have something called angle of a minimum deviation, delta mini. And when deviation is minimum, angle of incidence and angle of emergence will be equal. So we can write here twice I minus A. As a result, from this formula, we can write delta mini means angle of a minimum deviation plus angle of prism by 2 is the angle of incidence. So here I'm writing sine of angle of incidence. And what is angle of incidence? Angle of incidence is angle of prism plus angle of a minimum deviation by 2 divided by sine of angle of refraction. And similarly, at minimum deviation, minimum deviation. Okay, I'm not doing this all to confuse you. We'll preserve one formula, and when we go to that topic, you will automatically understand. At minimum deviation, that happens in prism, angle of prism will be equal to, actually angle of prism is equal to the sum of the two angles of refraction, because two refracting surfaces will be for a prism as the ray of light is incident and exits. There both the angle of refractions will be equal, and then angle of prism will be twice of R1. Instead of that, we can write angle of prism is equal to twice R, or angle of refraction is A by 2. So here in place of sine R, R is A by 2. So we can have an extension of this formula, which is in turn, actually we are trying to write a common formula for refractive index of one medium with respect to other medium, which is in turn, you see, we have this medium of separation. We have this medium of separation. And then what happened? We have a rarer medium and we have a denser medium. And then there is a coin, as I said. Okay, and we are trying to see this coin. When we try to see this coin from denser medium, the ray of light travels from denser medium to rarer medium, and it bends at the medium of separation. And here the observer is watching it, right? And then to the observer, it appears that this ray has not started from somewhere bent. It has started from somewhere a straight line somewhere. That means that exit or emergent ray, if you produce it forward, you will find the coin at a greater height. Then here, if I draw, yeah, here if I draw a straight line, this is say O, this is some, okay, A is already occupied, so I'll use some P and Q. So OQ distance is real depth. OQ distance is real depth, and OP distance is apparent depth. Apparent depth. Apparent depth means it appears to be there, but it is not there. So we can write a refractive index of one medium with respect to other medium as a real depth to apparent depth. So we can write it as OQ by OP. So this will be a common formula for refractive index of one medium with respect to other medium. So here we'll close this topic of refractive index. Okay. Right. Now what we'll do is, say, I'm listening.
Ma'am, could you re-explain that A by 2 is equal to R derivation?
Yeah, actually, you see at minimum deviation I've written no. So when the moment I come to glass prism, I will tell you that what is the deviation and what is minimum deviation. At minimum deviation, angle of incidence, angle of emergence becomes equal, and then we will get that I formula. At minimum deviation, the two angle of refraction become equal, and then we will get A is equal to twice R. So right now you can have one common formula, because when we go there, we can't come back here. That's why I kept one formula. Then I'll come back to this. I'll tell you the same points I'll write then also.
Okay, ma'am.
Right. So I'm just moving on. I'm just putting the screen up, and then I'll go for the next topic. Shall I scroll?
Yes, ma'am.
Okay. So here, after refractive index, we came to total internal reflection. We came to total. I'm actually recapitulating yesterday's work first. Total internal reflection, which is otherwise known as the principle the principle of reversibility of light. Reversibility of light. Principle of reversibility of light. And what it is? Principle of reversibility of light is the important condition is principle of reversibility of light is about say for example this we have a medium of separation, and when a ray of light travels from a denser medium to rarer medium, it bends away from normal. Okay, so we have a normal also. So at the point of incidence, arrow direction tells us which is incident ray and which is the refracted ray. So finally, we have this is angle of incidence and this is angle of refraction. Then further, what happens when at a certain, when we increase the angle of incidence, then at a certain angle of incidence called critical angle I subscript C, the angle of refraction will become 90. That means the ray of light is refracted along the medium of separation, angle of refraction becomes 90. So when a ray of light travels from denser medium to rarer medium, the ray of light bends, BENDS, away from normal at a certain angle of incidence, which is greater, at a certain angle of incidence, the angle of refraction becomes 90. That particular angle of incidence is called a critical angle. Now, what is total internal reflection? Total internal reflection is if angle of incidence is further increased. Angle of incidence is further increased. That means angle of incidence is greater than the critical angle. Then there is no more refraction because the refracted ray has already bent and it has passed by the medium of separation. So it has no more opportunity to be refracted. So it gets reflected into the same medium. So then when it reflects, then that law of reflection works. Angle of incidence is equal to angle of reflection. These two angles will become equal. Okay, and this phenomena is called total internal reflection or principle of reversibility of light. So here what were the conditions? Condition is a ray of light always has to travel from the ray of light always has to travel from denser medium to rarer medium. First condition for principle of reversibility, and angle of incidence should be greater than critical angle. Actually, critical angle is a constant. One material medium, one transparent material medium has one critical angle. I don't remember all of them, but critical angle for particular, because when I say glass, there are different types of glasses, just an average number I'm saying. Critical angle for glass is approximately 42 degree. That means here glass means a diamond is also included. That means whenever a ray of light is incident at an angle more than 42 degree in any type of glass, that ray of light is no more refracted. It is reflected into the same medium. Okay. That is, so this is what is about the principle of reversibility. And here we want, we will get one formula whose application. Say please.
And can we make any transparent material shine like diamond if there are that certain so that internal reflection takes place?
That's a nice point actually. You know, well-cut diamonds only shine bright. All diamonds don't shine bright. Actually, when they say diamond shine bright, it's not necessary that diamond shine bright. A well-cut diamond shines brilliantly. An ordinary diamond also, no, it is a broken piece of glass. So obviously it will have many plane surfaces and many pointed vertices. So in that way, diamond has, because you know what's very interesting is diamond, why it shines, there are many reasons. One, because its critical angle is 42 degrees, as I said. Not necessarily diamond, most of the glasses critical angle is 42 approximately. So when ray of light is incident into diamond, it is few rays will be incident inside it at an angle greater than 42. Then definitely those light rays get locked inside a diamond. Every time that ray of light hits the surface, some part exit and some part of the light gets internally reflected. In that way, the trapped light keeps on exiting in all directions and it appears to shine bright. That's one. Number two, refractive index of refractive index of diamond is highest, 2.42, which is the highest number. That means once a ray of light enters into the diamond piece, its speed just reduces. That means speed of light is lowest in diamond. It is so slow that it slowly internally reflects and slowly exits. And by the time our persistence of vision, that means our eye ability, our human eye persistence of vision is 1/16th of a second. It is called very less, okay, compared to many other creatures whose sensibilities are farther, faster or more. So our eyes happily catch those light rays, and for us it shines bright. Okay, this may be a reason, maybe it's still brilliant answers, maybe. I just felt these two are more suitable. Okay, right. Okay. So then here what happens, I'll take up a formula where we will connect refractive index of the medium and critical angle. Okay, so this is a common relation. This yesterday we derived actually, common relation. It doesn't matter if we spend some time on this topic because other topics are not that much intense. Numerical wise, solving wise also this helps. Common relation between a refractive index and a critical angle. So for that, say we have a denser medium. We have a denser medium and we have a rarer medium. And we have, yeah, I'm drawing a normal first, but actually we are not supposed to do so. So then we have the incident ray, and denser to rarer, it bends away from normal, so refracted ray. And then we have angle of incidence and angle of refraction, and this is the normal. Okay, so rarer medium is medium 1, denser medium is medium 2, say for example. So according to Snell's law, refractive index of second medium with yeah.
And we should take the incident medium as medium 1 now, ma'am.
Yes. Okay, okay. In that case, I'll do it in that way. Yeah, you're right, in fact. So this is medium 1, this is medium 2. So refractive index of, you're right, thanks. I'm wrong. So refractive index of second medium with respect to first medium is a sine of angle of incidence to sine of angle of refraction. So denser medium is first medium, rarer medium is the second medium. In the first medium, angle of incidence will be, in the second medium, angle of refraction will be. You are right. And then here, say the rarer medium is air, say for example, that's all, no special reason. And denser medium is some medium. Okay, it can be anything. So this is refractive index of a medium. This is refractive index of air. Right. And then what happens if this angle of incidence, if angle of incidence is further increased, okay, if angle of incidence is further increased to a certain angle for which angle of refraction is 90. Okay, then we have angle of incidence which is called critical angle for angle of refraction being 90. So we have refractive index of a medium by refractive index of air, which is approximately 1, which is sine of a critical angle. Just a moment, what I did. Mu2 by mu1 is sine I. I think I spoiled the show. Just a moment, Shakti. I don't think we are going to get like this. Okay. Denser medium is first medium. Rarer medium is second medium. Okay. Then refractive index of a second medium means what? Air to refractive index of the medium. Yes, this is the mistake that I did. Okay, so refractive index of second medium means air to refractive index of the denser medium is the sine of angle of incidence, and this time angle of incidence is critical angle to sine of angle of refraction. When angle of incidence is critical angle, angle of refraction has to be 90. Sine 90 is 1, mu air is also 1. So we have 1 by mu medium is equal to sine IC. So we can do some interchange of terms and we will have refractive index of medium is 1 by sine of a critical angle. So sometimes they will give us critical angle and we have to find the medium's refractive index. And if we remember the refractive index of few mediums, we can guess what medium it may be. Or refractive index of medium is given and we have to find a critical angle the way you saw in the example question. So until this we have discussed yesterday. Okay. So I'm moving on from this. Today what we are doing is we are about to learn refraction. We are going to learn refraction through glass slab, a rectangular glass slab. No, instead of going for refraction through glass slab, because just now I completed total internal reflection, then let us know that which are the devices which help in total internal reflection. I think after that, we will go for refraction through rectangular glass slab. Okay, so which are the devices that do or help in total internal? Actually, where do we use the concept of total internal reflection? We use it in optical instruments. That means we have certain optical instruments where we will use a certain kind of prisms which will help in totally reflecting a ray of light. And why we want Shakti, are you listening what I'm saying?
Yes, ma'am.
Exactly. So because we have completed the topic of total internal reflection, I will take up the next topic which is related to this only. Okay. Total internal reflection, this concept is used in certain devices like optical fibers, like total reflecting prisms. Okay. And what happens in these devices? These devices are generally used for optical fibers. As we discussed long back, it is used for long distance communication. Telephone cables there, or in surgeries, those all people use it. Optical fibers, at the end there will be a small camera and that is sent to the body. Those all in medicinal fields they use. Total reflecting prisms are used in certain optical instruments where a ray of light, once it is incident on the total reflecting prism, the ray of light can be sent out at 90 degrees or 180 degrees, or or as it is, just turning it upside down. Okay. And why shall we use a prism? We can use a mirror also, because mirror also can turn a ray of light by adjusting its position through certain angle. We don't use mirrors because mirrors may absorb some amount of light energy, and the exit light energy will be, its energy will be less. The image will be dimmer. But total internal reflection is a procedure where the total internal reflection of a ray of light occurs without much loss of energy for that purpose. Okay. So what are the devices that we use? We use applications of total internal reflection. Where is it applied? It is used in case of total reflecting prisms, total reflecting prisms, and it is used in optical fibers. Okay, so what are total reflecting prisms? Total reflecting prisms are actually, these are right angled prisms. In our laboratories, we will find equilateral triangular prisms that will deviate a ray of light from its actual path, and in the process, it disperses white light into a spectrum of 7 colors. Even no, it's not a right angle, it's an isosceles right angle triangle. Isosceles right angle prism. Isosceles right angle prisms also can do dispersion, but they will help us in doing total internal reflection more accurately. So for an isosceles, right angled prism means what? It will have, this is the base. It will have 2 congruent bases and 3 lateral surfaces. 2 lateral surfaces will be at right angles to each other. It will be like that. So here, how it helps in total internal reflection. When a ray of light is incident on this isosceles right angled prism. Okay, when a ray of light is incident and normal, if a ray of light is incident normal on a mirror or on a transparent surface, the ray of light, for reflection, if a ray of light is incident perpendicular to a mirror, it is reflected also in that, means angle of incidence, angle of reflection will be 0. For a ray of light, if it is incident along the normal on a transparent medium, then Snell's law fails. Snell's law fails means what? The ray of light is not bend at the medium of separation. So it won't bend. It will go straight. It will go straight and hit the other surface. Say, for example, this is the surface ABC. So this ray of light, which is incident normal, will hit AC, will hit AB normally, means perpendicular, and hit AC at a certain angle. Which angle? Say at the point of incidence, we draw a normal, then this angle will be 45 degrees. Okay, I think we can prove it also. Okay, this will hit at 45 degrees, and here it will be reflected with the same angle at 45 degrees. Because the ray of light is incident at 45, and I said that for glass, critical angle is approximately 42 degrees. For any glass, critical angle is 42. And if angle of incidence is 45, then the ray of light is, it gets internally reflected. Okay. So internal reflection occurs instead of the ray of light getting refracted and exiting. It won't exit. So it undergoes internal reflection, and the ray of light is incident on side BC perpendicular. So it just exits off. So this is that final refracted ray of light. And in this process, a total internal reflection of a ray of light occurs. The point is what? Ray of light incident on AB perpendicular. It hits the AC at 45 degrees. Because angle of incidence for the ray of light on surface AC is 45, it is more than 42. So there is no more refraction. There is total internal reflection, and the ray of light is completely bent through 90 degrees. So this is how a prism helps in reflecting the ray of light through 90 degrees. Similarly, it depends upon how, on which surface we incident the ray of light. The same total internal reflecting prism, total internal reflecting prisms are isosceles right angled prisms. So if the ray of light is incident normal to AC, say for example, the ray of light is incident normal to AC, then it hits the surface AB at a certain angle. Which angle? That angle is also, so here if I draw a normal, this angle is going to be 45. I think we can try to derive how it comes out 45, but it is going to be 45. And because this angle is greater than critical angle, the ray of light is not exited, like it will not get refracted. It will reflect into the same medium. It will reflect into the same medium. So angle of incidence 45 because internal reflection is occurring. So angle of incidence will be equal to angle of reflection. During total internal reflection, I and R, angle of incidence and angle of reflection will be same. That means in a way, the incident ray is turned at the surface AB by 90 degrees. And then this ray of light is incident on the surface BC once again at 45 degrees. And because once again the angle of incidence is greater than critical angle, this ray of light is internally once again reflected at the same angle 45. That means once again the ray of light is turned by 90 and this ray of light exits. So this is that emergent ray. So here the ray of light has completely turned by 180 degrees. So the first case, the ray of light is bent or rotated by 90, and in the second case, the ray of light is rotated by 180. Now, what is the purpose of rotating by 90 or 180? It depends upon what kind of optical instruments we are using. In periscopes, we want the ray of light to turn by 90 degrees when we have two prisms which are placed one at the eyepiece and one at the exit point. So the ray of light has to bend by 90. Okay, so it depends upon which optical instrument we are talking about. Okay, so total internal reflecting prisms are the prisms which will help us to rotate the ray of light through a certain angle. So 90, 180 are standard numbers, but we can bend the ray of light through various angles. But the condition is the ray of light has to be incident on a particular surface at an angle greater than 42. Then only. So these are the high end numbers. 90, 180 means in between numbers are also possible. Okay. Then we have the erecting prisms. That means non-deviating prisms. Actually, this is also non-deviating. The first two were also non-deviating. They were not no, they were deviating. In fact, they were not refracting. Okay. So how can we use a glass prism? This time, this prism need not be isosceles right angle prism. So I'm talking about any prism. This is the base of the prism, two bases and three lateral surfaces. So for this, when a ray of light is incident parallel to the base, say BC, then this ray of light, when it travels from one medium to another medium, it gets refracted. And this ray of light hits the surface BC at a certain angle. Which angle? At an angle which is greater than critical angle of glass. So say for example, this is some 45. If it is 45, what happens? Okay. If it is some other angle, accordingly the emergent rays exit and accordingly the image formation. So this hits the surface BC at 45. So angle of incidence is 45. So angle of reflection is also 45. Okay, because it has undergone total internal reflection. As a result, this ray of light emerges out parallel to the base BC. Okay, so say for example, this is incident ray P, emergent ray is Q. Let us have one more ray from the object. From the object, we can have a beam of light. Out of the beam of light, some two rays I'm taking, because for image formations, we take two rays. And this ray, after being incident on surface AB, it is refracted. And after after refraction, it hits the surface BC at a certain angle. At a certain angle, and that angle, if it is 45, if that angle, if it is 45, then the ray of light will not, then the ray of light will not get refracted. It will be uh, reflected. Total internal reflection occurs when angle of incidence is greater than 42. Total internal reflection occurs when angle of incidence is greater than 42. So say for example, if it hits the surface BC at 45, then angle of incidence and angle of reflection both will be 45. So the ray of light at the surface BC is turned by 90 degree, and finally it exits. And this is the emergent ray. So say the next incident ray is R, and this is the S. In the process, what happens? In the process, say the object is erect, its inverted image forms on the other side. So this is how the prisms are used for total internal reflection. It depends upon which optical instrument and how we want to make use of it. The first diagram was total internal reflection of a ray of light, which is turned by 90 degrees, next turned by 180 degrees, next the real image, real means the erect image is inverted. If you put an inverted image, it will be erect. Okay. Shakti, next what is used for total internal reflection is optical fibers. Optical fibers are actually bundles of glass or quartz, Quartz. A bundle, that means optical fiber. A fiber will have inside many fibers which are of nano diameter, and each of them is made up of glass or quartz. And when you really touch optical fibers, they are very much silky kind of thing. You can touch them, they are very soft and smooth. And when electromagnetic waves are incident through optical fibers, each nano dia fiber will take those incident electromagnetic waves, means light waves, and those light rays will undergo multiple internal reflection, means no refraction occurs. All the light rays that is incident, every bit of it undergoes total internal reflection. Means what? There is ultimately no loss of energy, no loss of light energy. With what intensity it is incident, it exits on the other end at the same intensity, same energy. And in the process, the electromagnetic waves travel long distances without no loss of energy. It is used for, as I said, long distance communication, or in the medical industry it is used. So, okay, so these were a few applications of this. Now we are, because that was about total internal reflection and where we use it. Total internal reflection, it is used in total internal reflection is used in periscopes also. Like, you know, when you were small, you must have seen periscopes where one end where we see, that end one plane mirror, and the other end where the object is there, the other end also one plane mirror. Those two plane mirrors are placed at the ends of the hollow cylindrical tubes, parallel but kept at 45 degrees to the ray of light. And light rays from the object will turn by 90, hit this mirror and turn by 90 and reach our eyes. But those periscopes which use mirrors and use the principle of reflection of light won't show the image of the object to that in clarity. But in place of plane mirrors, if total reflecting prisms, means isosceles right angled prisms are placed, then they will help in undergoing total internal reflection. And whenever total internal reflection occurs, there is no loss of energy, and you know, image resolution will be comparatively more than that of the mirror. Okay, so that's what I wanted to tell about total internal reflection. Okay, right. And then that you can just pass by this topic. It was not a very different topic. Okay, so we'll take up the next topic about refraction. Refraction through a rectangular glass slab. This is very interesting, as I talk about refraction through rectangular glass slab, and after this topic, I'll talk to you about refraction through glass prism. Okay, I'll take up equilateral triangular glass prism. Okay, that means when a ray of light travels through rectangular glass slab, what happens? And when a ray of light travels through a prism, glass prism, what happens? What's very interesting is a ray of light, when it is incident on a rectangular glass slab, it deviates from its actual path. Emergent ray will be parallel to the produced incident beam. But when a ray of light passes through a prism, it won't deviate from its actual path. In fact, it is deviated through a certain angle, due to which the ray of light breaks down or splits into a spectrum of 7 colors. Means what? Rectangular glass slab, though it is a glass medium, it doesn't produce that spectrum, whereas prisms produce a spectrum. You understand? That's very interesting. Sometimes they say that why rectangular glass slab doesn't disperse white light, whereas prism does. So what is the reason? Okay, that answer we'll get once we learn this. Okay. All right, so what is important is this is an experiment which is done in the laboratory. So first I'll tell you how this experiment is performed in the laboratory, and later on I'll talk to you about the details of refraction through a rectangular glass slab. So assume that ABCD. Assume that ABCD is a rectangular glass slab. Means it is rectangular, it is made up of glass, and it is a small slab. You take it like that. Slab means a piece of glass. And then AB is the incident surface and CD is the emergent surface. Okay, that one. So there is a ray of light which is incident on AB. So this is a straight line, in fact. No. This is that incident ray. So at point of incidence, we want to draw a normal. At point of incidence, there is a normal. Okay, normal means a line that stands perpendicular. Okay, and then we have angle of incidence. So what happens when you perform this experiment and prism ray diagram, actually schools compel to every child to do this, because when you do, you will see something very interesting. So what you people do is, in the laboratory, first you put a glass slab on the white paper and take a pencil and draw the outline. After drawing the outline, you will write A, B, C, D, the way I wrote. Then towards A, not in the middle or not towards B, towards A, you will draw an incident ray. And at the point of incidence, you will draw normal. So this much first you people do. And then what you people are supposed to do, or what your teacher will ask you to do is, on this incident ray, you have to put two ball pins vertically. On a drawing board, you place a white paper, and on the white paper, you place a glass slab, draw the outline, write ABCD, and then the incident ray. On the incident ray, you put two ball pins, P1 and P2, say for example. And then from the surface CD, you close one of your eyes and you try to see those two ball pins, P1 and P2, adjusting your head and eyes such that those two ball pins come in a straight line. And seeing those two, you put the ball pin 3 and the ball pin 4 with one eye closed. And later, once you put these two ball pins, or you mark with a pencil, in fact. Okay, and once you mark this point, actually you put ball pins only, sorry. So you will put P1, P2, P3 in a line, and P1, P2, P3, and P4 in a line. Once you do that, you take out the glass slab, you take out a ball ball pin P1, P2, P3, P4. And then you will take your scale and connect P3 and P4 to the surface CD.